Hello everyone, let's continue studying 3D graphics and we will see what we can get from it. I was thinking about some minor optimizations in the setup what we have. So because right now I realize something is broken, right? So if I would do, for example cubes, very first thing, and we would say example cube, it would not compile because it's cubes, but it still would not compile because there is two functions are missing. So function strafe and function look is missing. So what I'm going to do, I'm going to make the base example class, and I would give the interface. So let's see, last one was basic lighting, right? So we would have a class base example, and that would have 3 functions, and all of them are going to be interface probably. You know what we would do? We would do empty implementation to that. Okay, and we need to have destructor virtual destructor. Okay, and let's call it final as well here. Final, 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 final. Basic lighting, camera, final, colors, final, public, coordinate system. Hello triangle, load program shader tutorial. Textures. Transformations. So now it should compile and it should run as well. So it should have base cubes. One more thing. I think we should have template type name T a register function and I think const char star I guess string would be fine. String static, and we would have static stat unordered map, which would have stat string and stat function, which would return unique pointer of base example, include memory, so and here name we would do samples equals name equals stat make unique all constructors are same, right? So it takes this and we do T and pass all this stuff. We height. and we can have ctor, and we would do return w, and we can have wait a second, and we should, oh, what, memory file not found. So it should take those parameters and it returns this. Cool. Get examples list. Okay. I'm wondering why it's like this. Anyways, I think it's fine. Okay, now we need I guess we need some sort of macro Yeah, I'll figure out what kind of macro. Class base example reg t name, and this would do I'll do static, right? Static I think something like this, right? And we would do reg basic hmm no viable overload. Conversion from lambda to function we doing int. Huh. Oh, here we go. Okay, so we need that thing base example.cpp include example.hpp, and we need to get that thing base example Yep. So it's compiled. Now let's go to main and if argc greater than equal 2 and argv of 1 equals stat string dash h return 0 and for auto const e base example get examples stat cout e handle. I guess get example. Why did I put the list here? Oh, run dash h light. Okay. Um, examples cube. If argc less or equal 1, return make unique examples cube. Okay, and otherwise return base example c2 argv1 window with height. light. Okay. So this is the registration. Okay. So this is all these updates. So now I would not need to change main at all. It would be fully dynamic. So what I need to do, I need to create a class derived from base example, and I need to run register macro like this. So the type and name, and then I would be able just to run it like this, run try, and it would run this example. I guess that makes sense. So let's make the commit. Reorganize the project to make it more dynamic.
Reorganize the project to make it more dynamic.
So let's go to, so we are on materials.
In the real world, each object has a different reaction to light. Steel objects are often shinier than a clay vase, for example, and a wooden container doesn't react the same to light as a steel container. Some objects reflect the light without much scattering, resulting in small specular highlights, and others scatter a lot, giving the highlight a larger radius. If we want to simulate several types of objects in OpenGL, we have to define material properties specific to each surface. In the previous chapter, we defined an object and light color to define the visual output of the object, combined with an ambient and specular intensity component. When describing a surface, we can define a material color for each of the three lighting components: ambient, diffuse, and specular lighting. By specifying a color for each of the components, we have fine-grained control over the color output of the surface. Now, add a shininess component to those three colors, and we have all the material properties we need.
So we can specify it like this, right? Okay, let me first make the material, I guess. So this is our last sample. It's called basic lighting, and material. Let's call it materials. Basic and we would call this thing matte. So now compilation is a bit more optimized. Of course, it did compile all the shaders, and then it compiled only materials, and then is a linking stage. So run matte, and we have materials, and I'm pretty sure we can, just to be sure, let's update the fragment shader. We can do yeah, object color. So we can set, instead of coral, let's do so let's see if color will change. Yeah, now it's blue color. And if we would do light, yeah, so this is two different Now let's go to fragment shader and put that thing. So instead of object color, they're all back 4. It's object color, light color, light position. So it should be diffuse, right? Object color is not used anywhere. Oh, it does use. But there is a diffuse here. And there is ambient here. It's like, what the heck is going on here? I think it's still oh no, it's not running. It's failing. Expect reserve for uniform spec. Talking uniform. Ah, okay. So there is a semicolon here. Anyways, let's continue reading.
In the fragment shader, we create a struct to store the material properties of the surface. We can also store them as individual uniform values, but storing them as a struct keeps it more organized. We first define the layout of the struct, and then simply declare a uniform variable with the newly created struct as its type. As you can see, we define a color vector for each of the Phong lighting components. The ambient material vector defines what color the surface reflects under ambient lighting. This is usually the same as the surface's color. The diffuse material vector defines the color of the surface under diffuse lighting. The diffuse color is just like ambient lighting, set to the desired surface's color. The specular material vector sets the color of the specular highlight on the surface, or probably even reflect a surface-specific color. Lastly, the shininess impacts the scattering / radius of the specular highlight. With these 4 components that define an object's material, we can simulate many real-world materials. A table as found at duvernay.free.fr/curs/opengl/materials.html shows a list of material properties that simulate real materials found in the outside world. The following image shows the effects several of these real-world material values have on our cube. As you can see, by correctly specifying the material properties of a surface, it seemed to change the perception we have of the object. The effects are clearly noticeable, but for more realistic results, we'll need to replace the cube with something more complicated. In the later model loading chapters, we'll discuss more complicated shapes. Figuring out the right material settings for an object is a difficult feat that mostly requires experimentation and a lot of experience. It's not that uncommon to completely destroy the visual quality of an object by a misplaced material. Let's try implementing such a material system in the shaders. We created a uniform material struct in the fragment shader, so next we want to change the lighting calculations to comply with the new material properties. Since all the material variables are stored in a struct, we can access them from the material uniform.
Ambient light color times material ambient. Ambient. So we do not have ambient strength anymore. Light color times material dot ambient normalize normal, light direction normalize light position, and diff times material diffuse. Diff spec times material specular. Where is the shininess? Material, oh. And there is no object color, so we do not need object color, right, anymore. Okay, so set vec, set flow. Place by setting the appropriate uniform. It's not special name and setting struct only rely acts as namespace. Lightning shader. What the heck is this? Um set uniform. Hmm. I'm wondering if there is a way to do it like a secvec for. Let's see. Nope. Nope. Anyways, let's let's just do the way how we know to do it. So bjfx material ambient diffuse specular shininess. Now let's put dots in between and lowercase. Shininess is float. Doesn't like flow. Uniform types. Um, Interesting. Huh. Um, let's do it vex 4 for now. That's kind of interesting. So we put vec 4 here, and let's just put x. And we need to do it in the different order. I don't think it matters, but why not to make it look nice? Okay. So now we can set uniforms. Material, and let's where's the ambient 1.5.31 1.5.31 ambient diffuse 1.5.31 specular 5.5.5.5 and shininess 32. I think I can remove this stuff safely. I have like suspicion it's gonna be fine. Implicit cast from vec 4 to vec 3. Dot beans materials fc bin 35. Material diffuse. Okay, material diffuse RGB RGB 39 material specular default RGB. Still 3.9. Yeah, change it. Oh, wait a second. I need to update it. Spec. Uh, 3.9. Implicit cast from VEC 4 to VEC 3. I didn't get it. Why? Oh, segfault. Render update uniforms. So yeah, so we need to have all this data, otherwise it would segfault. Still segfault. One, two, three, four. 1, 2, 3, 4. 1, 2, 3, 4. So if I would not set lights. Okay, so if I uncomment this part, ambient, segfaulting. VEC 4. So if it has dot, it's would segfold. Huh. Interesting. So if I'll do it this way, it would be okay. I don't know. I don't know. Let's see. Struct. There is no. Oh, there is a model uniform. There is a struct. Ah, it's commented struct. So there is no structs in example, so I assume that shader language does not support structs. Does BGFX shader language supports structs?
Does BGFX shader language support structs?
No structs in uniforms. Inside the struct in BGS must be declared using uniform keyword. Uniform arrays, you can have structs of uniforms. You can have an array of vectors, which is standard way to pass structured data like bone transform. It's using shader storage buffer. You can use structs to map it. Okay. So there is no structs. It's okay. Light properties.
The object is way too bright. The reason for the object being too bright is that the ambient, diffuse, and specular colors are reflected with full force from any light source. Light sources also have different intensities for their ambient, diffuse, and specular components respectively. In the previous chapter, we solved this by varying the ambient and specular intensities with a strength value. We want to do something similar, but this time by specifying intensity vectors for each of the lighting components. If we'd visualize light color as vec3 1.0, the code would look like this. So each material property of the object is returned with full intensity for each of the light's components. These vec3 1.0 values can be influenced individually as well for each light source, and this is usually what we want. Right now, the ambient component of the object is fully influencing the color of the cube. The ambient component shouldn't really have such a big impact on the final color, so we can restrict the ambient color by setting the light's ambient intensity to a lower value. We can influence the diffuse and specular intensity of the light source in the same way. This is closely similar to what we did in the previous chapter. You could say we already created some light properties to influence each lighting component individually. We'll want to create something similar to the material struct for light properties. A light source has a different intensity for its ambient, diffuse, and specular components. The ambient light is usually set to a low intensity because we don't want the ambient color to be too dominant. The diffuse component of a light source is usually set to the exact color we'd like a light to have, often a bright white color. The specular component is usually kept at VEC 3 1.0, shining at full intensity. Note that we also added the light's position vector to the struct. Just like with the material uniform, we need to update the fragment shader. We then want to set the light intensities in the application.
Okay. Struct light. Light position, light ambient, use specular. Um, light diffuse and light specular. Okay, and let's see, 020202 ambient diffuse 555 and specular 111. Light pose. Yeah, now I need to fix the shader. Mm, ambient diffuse light diffuse light specular. So light color, diffuse color, ambient color. Okay, copy. So look, this light pose is completely so it's does not have to be diffuse color and ambient color. Use undeclared identifier light pause. So it should be outside of the loop. Translate. Yeah, can ignore could not much 3 against 4. How it was in the previous one, which was so it's vec free. GLM vec free. That's interesting. Okay, so we are going to be done with that. It's already 10:55 and I kind of feeling sleepy, so let me make the commit. So just the one chapter for today. Materials. Okay. Did I make the commit? Yeah, materials. Okay, thank you for watching, and see you next time. Bye.